have seen your normal generating functions, and we saw quite a few examples of them. And a very valid question you might be asking is, why are we looking at some complicated functions like this? Why are we looking at these generating functions? And the answer is, it helps us encode this really big infinite sequence that we would like into something that is slightly easier to handle. In Polya's words, who was a really big mathematician, um, it is more like a generating function is like a bag, right? You have all these thousands of coefficients that you could be worrying about or care about, and instead of individually looking at them, you're just carrying them all in this one bag, which is the generating function. And when you need them, you can just unpack things from your bag again, right? You can take out whatever coefficient you want by just looking at the generating function and taking it out. So we saw generating functions of the normal kind before. So now we'll look at what are called exponential generating functions. 7.3, exponential generating functions. So what are exponential generating functions? Similar to before, suppose you're given a sequence an. Well, I think the book uses hn, so let me also switch to hn. Suppose hn from n is equal to 0 to infinity is a sequence of real numbers, is a sequence of real numbers. The exponential function, the exponential generating function, of hn is denoted by g exponential of x, and it is similar to before, summation n is equal to 0 infinity hn x to the n over now a special n factorial. Okay, and so why is this the exponential generating function? Because, for example, if I take hn is equal to 1 for every n greater than or equal to 0, then my exponential generating function of this of x is equal to summation n is equal to 0 to infinity 1 times x to the n over n factorial, which, if you have seen this before, is exactly equal to e to the x. This is the expansion, power series expansion of e to the x. Okay, so let us look at some more examples. This was example, I'll just call them examples. Example, suppose hn denotes the number of permutations of 1 to n, the n permutations of 1 to n. Suppose hn is equal to the number of n permutations, n perms of 1 m, right? Find the exponential generating function. Find the exponential generating function. Answer. Well, hn is going to be, well, the number of n permutations of 1 to m. So for the first object, you have m choices. For the second object, you have m minus 1 choices, and dot dot dot. For the nth object, if you have m minus n plus 1 choices, right? Because this is a total of n things, which is exactly equal to m factorial over m minus n factorial, right? Well, therefore, uh, and hn is equal to 0 for every n greater than n, right? So it's a finite sum. It's not an infinite sum. We are looking at a finite sum. So my exponential generating function ge of x is equal to summation n is equal to 0 to infinity hn of x to the n over n factorial, which is equal to summation n is equal to 0 to infinity m factorial over m minus n factorial into x to the n over n factorial, which I can rearrange as, well, I know that hn is 0 after n is equal to m, so I will write this as summation n is equal to 0 to m choose n, x to the n, right? Because that's exactly what m factorial over m minus n factorial times n factorial is. And then this, you might recognize, is 1 plus x to the power n. I bet 1 plus x to the power n. Yeah, and so the the exponential generating function of the sequence is 1 plus x to the power m. Let us look at another example. Suppose I am looking at just a slightly, why we call it a general exponential generating function instead of 1a squared. Suppose I was looking at 1111. Suppose I was looking at hn is equal to a to the power n, right? It's a geometric series now. I am looking at a to the power n in everything. So my sequence looks like, for every n greater than or equal to 0. So my sequence looks like, not 0, 1 and 1 a squared dot dot dot, right? Then my g exponential of x is equal to summation n is equal to 0 to infinity a to the n x to the n over n factorial, which is equal to summation n is equal to 0 to infinity ax to the n over n factorial, which is equal to e to the power a times x, right? And so that is why we generally call it the general exponential generating function. And this is another example. Let us do a slightly more complicated example. Okay, so let us take a multiset where each element has some repetition. So consider the multiset S is equal to n1 times a1, n2 times a2, dot dot dot, nk times ak. So there are k types of different integers, and ni is the number of repetitions of it. Okay, and I am going to say hn is equal to number of n permutations, number of n perms of star, well, of S. right? And so this is slightly difficult to count. We want to find exponential generating function. This is not going to be super pretty, but let us try to work with it. Answer. So how do we do this? Well, in the first step one, choose n elements from this big set. Choose n elements from S. Well, how are we choosing n elements from S? We are choosing them in some order. B1 times A1, B2 times A2, dot dot dot, BK times AK. This is how I'm choosing them, where 0 is smaller than or equal to B1, smaller than or equal to N1. 0 smaller than or equal to B2, smaller than or equal to N2, dot dot dot, 0 smaller than or equal to BK, smaller than or equal to NK, right? This is the maximum size, and B1 plus B2 plus dot 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 is BK should exactly be equal to N, right? We are trying to choose exactly N of these. Then suppose I have chosen them in this order, then how many ways do I have? Step 2. How many combinations can I make of these? How many permutations, orders do I have? So the permutations, the number of permutations, the number of n permutations, well, not n permutations, just permutations, I guess. Number of permutations of these n elements is equal to n factorial, that's the total number of arrangements, divided by the number of arrangements where I can interchange any of these, right? So b1 factorial times b2 factorial times dot 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 times bk factorial. Okay, we have seen these before. And so therefore hn is equal to number of n permutations of S, n permutations of S is going to be the summation over something, question mark, n factorial over b1 factorial times b2 factorial times dot 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 times bk factorial. Right? And now what is this summation over? What is this question mark? This is the sum over all the ways of finding my b1 to bn, all the sequences b1 to bn. Sum over all sequences b1 dot 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 bk, sorry, not n, bk, such that 0 smaller than or equal to bi smaller than or equal to ni for every I from 0 from I in 1 to k. Right. Great. With the added condition with b1 plus b2 plus dot 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 plus bk is equal to n. Right. This is what the sum is over, which is slightly hard to count, and I don't really know how to do it. But I'm going to, for now, be like, okay, I will put this thing in it directly and see how my life goes. Therefore, the exponential generating function of x is going to be summation n is equal to 0 to infinity hn x to the n over n factorial, which is equal to summation n is equal to 0 to infinity summation over my sequence of bi's, summation 0 smaller than n smaller than or equal to ni, b1 plus b plus bk is equal to n of n factorial over b1 factorial times b2 factorial times dot 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 times bk factorial, all times x to the n over n factorial. Once again, technically this is a finite sum, okay? Because if my n is more than n1 plus n2 plus n3 plus nk, then the sum is 0, right? So I can do this. I can cancel these, and I have this summation. Well, you have seen this before, that this is exactly, well, saying I am looking at summation, well, what are the possible values? b1 goes from 0 to n1, b2 goes from 0 to n2, dot dot dot, summation bk goes from 0 to nk, x to the b1 plus b2 plus dot 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 all the way up to bk over b1 factorial multiplied by b2 factorial multiplied by dot 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 multiplied by bk factorial. Whew, not super pleasant, but what this allows me to do, writing it like this as a k-sum, is I can split it into different sums. We can write it as summation b1 is equal to 0 to n1 x to the b1 over b1 factorial times summation b2 is equal to 0 to n2 x to the b2 over b2 factorial times dot multiplied by dot 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 multiplied by summation bk is equal to 0 to nk x to the bk over bk factorial. Okay, great. And now it becomes a question of, well, are n1s, are nk's finite or they are not finite? Okay, I'm going to say I don't care. I am going to say fn of x. Let me actually go with m. Maybe I don't want to use n again. Fm of x is equal to define fm of x is equal to 1 plus x squared plus 1 plus x over 1 factorial x squared over 2 factorial plus dot 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 x to the m over m factorial if m is smaller than infinity, if e to the x if m is equal to infinity. Okay, if I define it like this, then all these sums of bi's that I have over here just becomes f of fn1 of x multiplied by fn2 of x times dot 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 multiplied by dot 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 multiplied by fnk of x. Right? Now, yes, I don't have this in a very standard, oh, look at this. This is the perfect thing I have from this convenient function I have from before kind of thing. But it's in a standard form. Like I can solve for these pretty easily rather than having to calculate my random things, right? So I'll stop this part here.